Hello, welcome to this video where I'm going to talk about Bitcoin smart contracts. Now, you probably heard about smart contracts before in the context of other cryptocurrencies such as Ethereum. What's probably less well known is that we actually have support for smart contracts in Bitcoin. One of the main reasons you don't hear about that very often is that they're quite limited. However, that's also a benefit because it's easier to explain Bitcoin smart contracts, so it's a good introduction to smart contracts in general. And if you're interested in this, I'd advise you to look at this explanation before you're looking at how other smart contracts look. But first of all, what exactly is a smart contract? I think that the name is a little bit confusing and contributes to creating a bit of a mystery of what a smart contract is. When you hear the word contract, you think about something that you draft up with a lawyer, and in some sense it is that in that it's written in code, but I think that thinking about it this way is probably going to confuse you more than it needs to. Instead, I think it's a lot easier to think about smart contracts as simply script or code on the blockchain. Now, if you haven't seen my previous videos, you might not know exactly what a blockchain is, so I advise you to look at that first, because I'm going to talk about transactions and briefly blockchains, which is needed to understand what I'm going to be talking about here. Usually a smart contract is part of the transaction. That's the case for Bitcoin, and I believe it's also always the case for Ethereum. They're not code that just keeps running like a web server. Rather, they're run in response to something, such as performing a transaction, which is the case for Bitcoin. And they describe conditions which must be true to release coins. Before I look at how this works, I want you to look at, just get an idea of how the script language works in Bitcoin. Now, it's not written exactly as I show you here. There's not really a push operation that I show you, but there are operations for putting data on a stack. But conceptually, this is how it works. If you're familiar with other programming languages such as Python or C or C++ or Java, then you would be used to having variables that allows you to say you can add a 3 plus some variable foobar. Well, you don't really do that with Bitcoin script. Instead, all the operations operate on a stack. So what we do is each instruction here is this first instruction is going to push some numbers on top of the stack. And then you can see that add, it doesn't specify what numbers it's operating on. Instead, what it does is it pops the two top elements of the stack and adds them together and pushes the resulting number on top of the stack. Equal works similar, except in this case, it takes the two top elements and compares them and returns a Boolean element, which will be true in this case, depending on, of course, on whether the numbers are equal or not. However, it's more interesting for us how we can use this script to facilitate transactions in Bitcoin. So we're going to look at this case where we're going to look at transaction T3 here in the middle and how it's used to perform a transaction where we're spending outputs from transaction T1 and T2 going to the holder of the purple public key or Bitcoin address, which is I'm going to refer to as Alice in this case, and we're sending 2 Bitcoins to Bob in green here. So these are the 2 unspent outputs of the transaction. In my video about Bitcoin wallets and transactions, I'm going through more of the details about how this works with outgoing unspent transaction outputs. But this is a little bit of repetition of what I talk about here. For instance, you can look at the transaction as a data structure. This gets stored on the disk inside the individual blocks in the blockchain. So T3 in this case has 2 inputs, T1 and T2. And we need a column for the index because each transaction could potentially have multiple outputs. And each one of those outputs are given an index. So this is how we're referring to the index. Now, T1 and T2 only have 1 output each, so they're all on index 0. And then we have a signature for this transaction. But I'm going to show you that later how that works. This is essentially some code. You can see there's two outputs for this transaction. So they're given a different index 0 and 1. The first output goes to Bob, so that was colored in green, and it's 2 Bitcoins. And then the change goes back to Alice again, which is a total of 2 Bitcoins. Creating this transaction relies on having a signature for the transaction. We're going to be using that in the scripts that I'm going to be looking at, so it's worth revisiting how these signatures are created. So we take as an input the previous transaction as well as the outputs that we're taking. So here I say Bob's public key and Alice's public key, and more specifically this is going to be the Bitcoin address of Bob and Alice. Conceptually this is almost the same, which is why I put that here. This information is concatenated and hashed to get what we call a digest, which is again encrypted using Alice's private key, which gives us the final signature. Now the signature cannot be created in this way unless we have this particular information in the transaction and we had access to Alice's private key. So in a way the signature proves that Alice has authenticated this transaction. But there's a lot of flexibility in how we use the signature, which is what we're going to see when we go through the code. What I'm going to show you is how Bitcoin transactions are normally verified. There are a lot of possible variations. You could do it in different ways. In this case, we're going to look at input and outputs. And the input in this case is going to be one of the inputs on the T3 transaction. And the output, there can be many outputs that we're connecting to an input, but we're going to consider an output from the T1 transaction. Or you can just assume that's what's going on. So we have an input and output, and for each input and output, it's not merely data, but it is actually code that we got here. So for the input, we have an instruction that pushes the signature. So this is Alice's signature that you saw earlier. And I'm saying I'm pushing 516, which represents the signature. Obviously, in real life, this would be a much larger number, but this is just to make it easier for you to remember which signatures I'm referring to. And then we have push 606 on the stack, and 606, I'm using that just to represent the public key. And again, that would be a much longer number in real life. The output contains a number of instructions, a duplicate, which will duplicate whatever is on top of the stack, hash, which in the Bitcoin manual will be referred to as hash 160, which if you supply on the top of the stack a public key and you hash this, you will get the equivalent Bitcoin address. So if you give it Alice's public key, it will produce Alice's Bitcoin address. And 112 is what we're going to use in this example to represent Alice's Bitcoin address. Equal verify is similar to equal, except we're not pushing a Boolean value on top of the stack, but this is used to verify and decide whether we're going to continue running the scripts. And finally, we got check sig or check signature, which is the final instruction that has to go through. I'm going to talk more in detail later about how that works. So let's run through this program. What you can see is that we actually concatenate the input and the output. So what I said earlier is that the output basically represents a challenge that has to be met with the input. And we meet that by prefixing the program with the inputs code. For some reason, when I started reading about this seemed a bit unnatural to me, because I figured since the input, that belongs to the transaction that comes last. So you imagine, why shouldn't you append that? But if you think about it a little bit, the output is representing some challenge that has to be met. Well, that challenge needs some kind of inputs, right, that it has to process. And if we appended this, there'd be no way of that code to process it. So this code has to go in the beginning. So we start by putting the signature on top and then the public key. And duplicate will duplicate the public key. And then we're hashing the public key so that we get the address. And now in the challenge, we have put in Alice's Bitcoin address. This is where we're sending the money. And now we can actually check whether this public key corresponds to the address. So that's an important verification, because now we have the public key here, and we know that this one can be used to check the signature. That's on the bottom. So I'm going to show you now, when you run checksig, will take these as arguments. And I'm going to show you a little bit more in detail how that works. Checksig takes several arguments, not just these ones. The first one is the transaction itself, T3, the counts of that. And then what we saw, we got from the stack, the signature and the public key. So what happens is that you take the transaction and hash it, and you get a digest. Now, if you decrypt the signature using Alice's public key, if you have signed this particular transaction with Alice's private key, you're supposed to get the exact same digests back. And when you compare these two and they're equal, you know that you got a valid transaction. The great thing about this system of actually using code rather than hard coding, how this comparison works, is that you have a lot of flexibility in creating different kinds of challenges. You could, for instance, create an output script that requires multiple signatures. So you can create, for instance, an escrow service. So far, I'm giving you an overview over how the Bitcoin script language works. However, if you want to get more details about how this works and all the various operations that exist and which you can utilize to create more advanced smart contracts, you can look at this wiki page for the Bitcoin system. Here we can see a description of the script language. If you scroll down, you can see all the different operations that you can use covered, even details like how they're actually encoded in raw form inside the Bitcoin transactions, as well as descriptions of what they do. Let's look at an example, which is what we already looked at and how they're represented here. So what they do here is that they call script pub key, is what they will usually use as terminology to refer to the output script. You can see that here. Script public key is the output of the previously unspent transaction, whereas script sig is the input of the spending transaction, which you can see here. So opdup means the duplicate operation, and then we have the hashing operation that I showed you previously that will hash the public key. And this is a placeholder for the Bitcoin address or the hash of the public key. And then we have the equal and verify operation that checks whether the Bitcoin addresses on top of the stack are equal. And then finally we have the check signature. Now in the raw form, of course, we're not storing these. These are basically just defines or symbols. In fact, these are representing these individual hexadecimal numbers that actually get stored in the transaction. So this is, for these two scripts, we get this in the raw form stored. Let's do a recap of what I've gone through here. So the outputs from transactions basically is code that represents a challenge to whoever wants to spend that money on that output. The input then contains code to meet that challenge. And so the input and the output code gets combined and run as one block of code to verify the transaction itself.